EM is short for expectation maximization. Those are the two steps within each iteration. We're going to have an expectation step, that's like one part of the coordinate ascent algorithm, and then a maximization step, which is like the second part of a coordinate ascent algorithm within one iteration. Okay, so I want to discuss this in the context of a motivating example, a simple example where EM can be used. And then we're going to see how the EM algorithm can be used for this problem. So this is the problem where we have missing data, and in particular a certain type of missing data with a certain model assumption. So let's imagine that we have data x1 through xn, and xi is in each x is in Rd. Except it's now a vector that has missing values. We have a vector, each vector is in Rd, but for each vector there might be some values that are missing. And these values don't form any pattern. Some data can have many values missing, some data can have no values missing, and the dimensions along which they're missing is totally random. So there's no pattern in the way that the data is missing. So let's split this vector xi into two parts. We'll call xi o, the observed portion of the vector. So that's the subvector that we get by taking the observed values of xi and forming a smaller vector corresponding to the observed values. So xio only has measured values in it. And then xim is the missing portion of the vector xi. So this is a subvector where we don't know any of the values in it, and the dimensionality of each of these can change for each I. So we have to make a model assumption in order to use the EM algorithm, otherwise it's not going to apply. And our assumption is that each of these vectors xi are generated IID from a multivariate Gaussian with mean mu and covariance sigma. So we're going to make this modeling assumption. Each xi is generated IID, and then after it's generated, some of the values, for whatever reason, go missing. Now our goal is going to be to solve this maximum likelihood problem, where we want to find the maximum likelihood values for mu and sigma, where we only can take the likelihood over the observed portion of the vector, because if we don't have any of the data in a missing portion, then we can't factor it into the likelihood. So we want to maximize the log of the joint likelihood only over what we observe. So we'll quickly see that this is tricky. It's not impossible, actually, but it's tricky because each of these xios can have different dimensionality, and those dimensions can correspond to different subsets of the dimensions in mu and sigma. So it's not something that we can simply directly take a derivative of and set to 0. However, we think that if we knew the missing portion, so if we knew xim, if we had values for those missing dimensions, and therefore we knew all xi, then we could easily maximize this thing. So we can take the argmax of the log of the joint likelihood of the observed and missing portion over mu and sigma. That's actually what we've already seen on a previous slide, but that assumes that we know the values in this missing portion of the vector. So I want to connect this now to a more general setup. What we're going to return to in a later slide is an algorithm, an EM algorithm, for optimizing this thing over mu and sigma, and also simultaneously imputing the values of all of the missing portions of each vector. So the EM algorithm is going to give us a technique for actually optimizing this thing and also filling in all of these missing values. However, I want to discuss it first in the more general setup. So what we are now going to imagine is we have two parameter sets, theta 1 and theta 2, where theta 2 in this model relates to theta 1 in the following way, that the marginal distribution of x given theta 1 is equal to an integral of a joint distribution of x and theta 2 given theta 1 over theta 2. So the distribution on x given theta 1 is equal to the integral of this joint distribution. So this theta 2 is like a hidden variable or a missing latent auxiliary variable that we don't get to observe in the data. So for example, if we want to return to the missing data problem, we can see that this likelihood, what we want to maximize over the observed portion of the vector, and where theta 1 could be the set mu and sigma, is equal to the integral of the joint distribution of the missing and observed portion. So this is a multivariate Gaussian with mean mu and covariance sigma, but now we integrate out a missing portion of the vector. So we can write this distribution as an integral over the missing portion of the vector, and that's equal to we can show, I'm not going to derive it, but we can show that that is equal to a multivariate Gaussian, where the mean is equal to the portion of the mean vector restricted to the observed dimensions, and the covariance is equal to the submatrix formed by only considering the observed dimensions. So this is a common derivation and very useful derivation of working with multivariate Gaussians, where if we want to integrate out a subset of the dimensions of a multivariate Gaussian, we simply get a Gaussian back with mean and covariance equal to their appropriate subsets. So now we need to define an objective function, as always, that's going to give us what we want. So what we want is a way to optimize the marginal distribution, returning to the more abstract parameters and notation, that allows us to maximize this distribution of x given theta 1 over theta 1, where theta 2 is nowhere to be seen, but that it uses this joint distribution, it uses this additional variable theta 2 to help us maximize this thing for computational reasons. So again, we're going to stay abstract and make it more concrete in the context of missing data later. To achieve these two objectives, using the EM algorithm, we form this equality. And so I'm going to pick this apart in the following slide. But for right now, I just claim that the left-hand side, which you notice is what we want to maximize over theta 1, is equal to this right-hand side. And notice that the right-hand side involves this joint likelihood over an additional variable theta 2. It also involves the conditional posterior distribution of theta 2 given x and given theta 1. And it also includes this additional probability distribution q on theta 2. Okay, before I pick this apart, I want to make a few immediate comments. First, what we're going to do, what the EM algorithm does, is instead of working with this left-hand side, it's going to work with this right-hand side. And it's going to specifically define an algorithm for working with this right-hand side such that we end up with a value for theta 1 that gives us a local maximum of this left-hand side. So we're going to actually optimize this left-hand side without ever using it, without ever working with it. We're going to optimize this left-hand side by working with this right-hand side. A second thing to notice is that this q, this mysterious q distribution on theta 2, is a probability distribution, and in principle, it can be any probability distribution that we want on theta 2, as long as it's defined on the values that theta 2 can take. However, the EM algorithm is going to tell us how to set this q distribution. Also, if we're looking at this right-hand side and saying that we want to somehow work with this thing because it's easier than working with the left-hand side, that's going to imply that this missing variable theta 2, that the conditional posterior of it can be calculated given x and theta 1. So this conditional posterior, we're going to assume is going to be something that we can calculate in closed form very easily. Okay, so first let's show that the equality is actually inequality. This is just a copy of what was on the previous slide. We want to basically prove that this side is equal to that side. So first, to do this, what we're going to do is combine these two things. Recall that the log of a product of two terms, so we have this term and this term, the log of the product of two terms is equal to the sum of the log of each term separately. And so we've taken this integral and this q and combined this term here and this term here, and then written the sum of these two logs as a log of a product of what's inside the logs. So these two terms are equal to each other. We immediately get to cancel these two things out. Next, let's remember some rules of probability. We saw in a previous lecture that if we wanted to find the probability of A and B given C, we can equivalently write that as being equal to the probability of A given B and C times the probability of B given C. So we can write this joint probability into a conditional probability times another conditional probability. And so since this is true, we can now solve for B given C by dividing both sides by this term to find that the probability of B given C can be written in this way. So notice that there's an A on this side, but there's no A on this side. Okay, so now I notice that I had a typo here. Let A equal theta 2, B equal x, and C equal theta 1. Plug those into the right-hand side here. And you'll notice that the right-hand side is equal to this term. And then using the rules of probability, we can say that the right-hand side is equal to the left-hand side. So we can take this term and replace it with this term where B is equal to x and C is equal to theta 1. And we get this here. So this complicated term simplifies into this term here. And then finally, there's no theta 2 here, so we can bring this term out front. We can bring this term out front, and then whatever q is equal to. And so this is why it doesn't matter what we define q to be equal to. As long as it's a probability distribution, the integral of a probability distribution equals 1. And so we're left with this. The left-hand side is equal to the right-hand side trivially. So we've shown that this term is equal to this term. So now the question is, why in the world would it be easier to work with this right-hand side, this much more complicated right-hand side, than this much simpler looking left-hand side? And so that's the genius of the EM algorithm. Now let's focus in on these two terms a bit more. So we've taken our log of our likelihood of x given theta 1, and we've written it into the sum of two different terms. First, let's look at this term here, the first term. Notice that once we define q of theta 2, this term is actually only a function of theta 1 because we've integrated out theta 2. It's also a function of the data, but we plug that in. We don't change the data. We change theta 1. And so this thing, actually, even though it looks like it has theta 2 in it, once we solve it, theta 2 will be integrated out, and we'll only have a function here of theta 1. So that's the crucial observation number 1. The second crucial observation is that this second term is a function that that's very famous, widely used, and has a name. It's called the Kullback-Leibler divergence. So this can be thought of as like a distance measured between two probability distributions. It's not a proper distance because it doesn't satisfy the triangle inequality. However, it can be thought of as a distance for two key reasons. First, we can show that this term is greater than or equal to 0. No matter what the probability is here, and no matter what the probability is here, this integral will be greater than or equal to 0. So that requires a proof. It's not at all obvious. You can't look at it and see that that's true. We need to have a proof to show that this is the case. but the proof does show that this term is always greater than or equal to 0 for every possible probability distributions that you plug in here. Similarly, it's only equal to 0 when these two distributions are equal. So when Q is equal to P, when this distribution is equal to this distribution, then the KL divergence equals 0. And that's the only case where it equals 0. And then more intuitively speaking, we can think of when the distribution Q overlaps more with the distribution P, the KL divergence gets smaller. And then as the two distributions get farther and farther apart, the KL divergence gets bigger. But for our purposes, the only two important properties are that this is always positive or equal to 0, and it only equals 0 when this distribution and this distribution are equal to each other. Okay, so we're going to see how we can use those two terms to optimize the log likelihood of x given theta 1. But before we do that, I first want to ask, what does it mean to iteratively optimize this function with respect to theta 1? So what is it that we're looking for when we say that we want to maximize this thing, when we say we want to come up with an algorithm that's going to maximize this thing? So one way of thinking about it is to say that we're looking for an algorithm, we're looking for a sequence of rules to follow such that we get a sequence of values. The algorithm will output a sequence of values for theta 1 where the log of the probability of x given theta 1 at iteration t for any t is greater than the value of the log of the probability of x given the value of theta 1 at the previous iteration. So these values for theta 1 are being output to us as a function of iteration, the first, second, third, and fourth, etc. iteration. And if we plug in the sequence of values, we're monotonically increasing this log likelihood. So that's intuitively what it means to optimize this thing. We also have to then prove that that sequence is converging to a local optimal solution. In this lecture, what we're going to do is show how the EM algorithm gives us this. It's going to give us a sequence of steps to follow so that we're continually finding new values for theta 1 that are increasing this log likelihood. But we're not going to discuss theta 2 that shows that the sequence also converges to a local optimal. And so intuitively, if you want to know what that means, you could think of it this way. If this is what we're trying to maximize, so imagine that this is the maximum point right here. We want a sequence of values, theta 1, 1, and then a second value, theta 1, 2. We want a sequence of values such that we're always increasing, we're always finding new values that are better than the old values. However, you can imagine that there's a point here where we're continually having our distance to this point. In that case, we're always finding points that are monotonically increasing the objective function. However, it's actually converging to this point here. So that's like a thought experiment that you can do to show that it's not enough to say that you're always finding better values. You also have to show that those values are converging to a local or a global optimal value.